Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 43, we will cover the second part of runoff estimation. The different concepts that we will cover are the SCS-CN method, and within the SCS-CN method, what are the different factors determining CN values, curve number selection. Then we will look into the time area method, the unit hydrograph method, and we will also look into some other methods as well. So, the SCS-CN method is an alternative to the rational method that we learnt in the last lecture, and as you saw that there are several assumptions in the rational runoff method, and which makes it which makes it unusual for a little bit larger catchments maybe, and also in certain other cases when we instead of just urban area, we have a mix of urban and other kind of areas, like a lot of greenery is there and so on. So, the SCS-CN method is particularly developed in the US, and the method is the difference, the values that has been computed in this particular method is as per US standards, but many Indian researchers, many Indian scientists have also used this method with certain modifications to it, of course, and they have applied it for Indian catchments as well to estimate runoff in Indian catchments, right. So, this particular method is appropriate in case of runoff for long duration, high intensity rainfalls over small drainage basins. But even small drainage basins means it could be even larger than urban catchments, right. For high intensity rainfalls and also for rainfalls of longer duration, this is a more appropriate method. And this was developed by the US Soil Conservation Service, USCS, and SCS, and then for estimating runoff volume for US conditions. And this was developed during 1969, then it was further worked upon and then modified as well later on. So, the first concept that is there, that is runoff in this particular method, it is assumed that runoff starts after an initial abstraction. Initial abstraction means in this particular graph, you can see that on this axis we have got time, and on the y axis we have got precipitation, and what we see that the first part, the first for the little bit of time, we have got IA, which is initial abstraction. That means this is the rainfall that happens, but this rainfall is not creating any sort of runoff. So, this is initial abstraction. Why? This is because of interception, surface depression, storage and infiltration. So, initially even if runoff starts, before that when rainfall falls, immediately some amount of it percolates, some amount of it is stored on the depressions in the ground. So, no runoff is formed for a little bit of time. So, that is the initial abstraction period. So, this initial abstraction is first considered. Then after runoff starts, some rainfall is lost in form of infiltration. So, that means even after some runoff starts, then what happens, some amount of rainfall goes into the ground, and that means there is continuous percolation inside the ground. So, there is infiltration in the ground, and this is called actual retention, similar to the concept of this coefficients for that we have dealt with in the rational formula, and the rest of the volume goes as could be generated as runoff. And as you can see in this chart, whatever falls within this area, this is the infiltration volume. The rest is the volume that generates as runoff. So, and then there is change in the intensity of rainfall at different time periods. So, this volume is basically the volume that we are concerned with. So, this is the one which creates the runoff at the inlet point. So, the actual retention increases with increase in rainfall up to some maximum value, which is potential maximum retention. So, that means even if the rainfall keeps on happening, then at one point of time there is no further retention. So, it has got a potential maximum value. So, this is also not considered in the rational method, because we assume a constant C value. So, a constant this coefficient which assumes that a part of the rainfall always is lost, but here some part of the rainfall after a certain time is not lost, there is no further loss. So, as you can see, the infiltration gradually goes down and eventually it may not be there as well. So, the ratio of actual retention of rainfall to the potential maximum retention S is equal to the ratio of direct runoff to runoff minus initial abstraction. So, this is given by F by S, where F is actual retention, S is potential maximum retention, this one is equal to Q accumulated runoff depth. Runoff is measured in depth, that is depth of rainfall. Suppose there is a surface area, whatever rainfall falls we measure in millimeter. So, that is the total rainfall. Similarly, we can take part of that and part of that depth and say that this part of the depth goes as runoff. So, runoff is also measured as depth. So, Q is accumulated runoff depth and P is accumulated rainfall depth, that means the actual rainfall, and then minus IA, that is initial abstraction. So, once after initial abstraction whatever is left, part of that becomes the runoff. So, this proportion between that runoff and that rainfall minus abstraction is same as retention divided by potential maximum retention. So, this is the formula that is used, and after runoff starts, all additional excess rainfall becomes runoff or actual retention. So, after initial abstraction either it becomes runoff, rainfall, or it becomes that infiltration or retention. So, actual retention is the difference between rainfall minus initial abstraction and runoff. So, actual retention is whatever goes into the ground is runoff minus rainfall minus initial abstraction and runoff. So, if I take out runoff as well as initial abstraction, whatever is left is this actual retention. So, F is equal to, which is actual retention, is equal to P minus IA by Q. Now, combining these two equations, we get Q equal to P minus 1A whole square by P minus IA, IA whole square by P minus IA plus S. So, that is the simple relationship that we can develop. Now, based on certain regressions and certain empirical relationships, we have found that even though it varies for different AMC conditions and soil type, AMC means antecedent moisture condition. That means what amount of moisture is there already in the soil. And also depending on soil types, this relationship varies, but IA, that is initial abstraction, is equal to 0.2 S. S is potential maximum retention. So, 0.2 of S, that is of retention, is equal to IA. So, IA is 0.2 times of S. So, that is a relationship which has been developed via regression. So, now if this is replaced in this particular formula, we get Q equal to P minus 0.2 S whole square divided by P plus 0.8 S, and this for assumption that P is greater than 0.2 S. So, what is Q? Q is accumulated runoff depth, P is what? P is accumulated rainfall depth, and S is what? Potential maximum retention. So, for P greater than 0.2 S, that because I we have already taken is equal to 0.2 S. So, P when it is greater than 0.2 S, then this equation stands. So, then the rainfall runoff relationship is basically the relationship between rainfall depth and potential maximum retention, which is given in inches or it could be even given in millimeter. So, S, that maximum retention that is possible for a particular area, depends on characteristics of soil, vegetation, land use and antecedent soil moisture conditions. So, this first part, that is soil type, vegetation type, land use type, is called the SVL complex, because it is a complex value for all these three parameters, and antecedent soil moisture conditions determine how much already water is there in the soil. So, this two determines the relationship between rainfall depth and the potential maximum retention. That means, how much water will infiltrate into the ground depends on all these factors. So, S value, that is this value is converted to a curved number which is dimensionless parameter. So, for each of this S value a curved number is being generated, like for paved areas where S equal to 0, that means potential maximum retention is 0 for paved areas. So, Cn curved number is 100. So, in this particular image you can see the different curved numbers, like this is Cn curved number 100. Similarly, for highly permeable flat lying soil, S is equal to infinity, where Cn value would be 0. That means, where no amount of that means everything is getting infiltrated. So, there Cn value would be 0. So, all rainfall will infiltrate and there will be no runoff. So, we have got this basic relationship S equal to 100 divided by Cn minus 10. So, based on that the Cn number is given. So, Cn number is equal to 1000 divided by S plus 10, where S is in millimeter. So, this S value could be estimated from Cn curve. So, if we know the Cn curve for a particular area, then we can calculate the S value and we can put it in the equation, and then we can get Q value, which is the discharge value. So, this is how the SCS-Cn method works. Now, the next thing is, how do I determine this Cn value? So, this Cn value is given like this, and we can, from the Cn curve, this is the curve, you can see along that particular curve. Suppose I take for this value of 100. So, that means everything is like for a value of 100, that means for paved area everything becomes runoff. So, for a 50 amount of rainfall in millimeter, the direct runoff in millimeter is also 50. But for Cn curve of 95, for a value of 55, the runoff is still 50. For a curve of 40, for a value of 40, for a curve number 40, to generate 50 mm of runoff, actually rainfall is around something around 240. So, 240 millimeter of rainfall becomes a curve of this one. So, that is how the relationships, the curves are being developed. Now, the next question is, what curve number should I select? So, that depends on this curve number depends on this characteristics of soil, vegetation, land, as well as this soil moisture conditions. So, first of all, let us look at the antecedent moisture conditions. So, this is the relative moisture of pervious surfaces prior to the rainfall event, for which we are estimating the runoff. So, that means for any rainfall event we will be estimating the runoff. So, before that, 5 days before that, rainfall in immediate past 5 days determines that what would be the antecedent moisture condition of the soil. So, if antecedent moisture in the last 5 days during different seasons, like dormant season, these are crop growing seasons, this is as per the SCS-Cn method, then growing season, then average season, the rainfall millimeter value is 2 or 3 or 4, it falls in class number 1. If the rainfall value is lesser than 13, this is just number of the columns. This is lesser than 13 or lesser than 36 or lesser than 23 for these 3 seasons, it falls in antecedent moisture condition class number 1. Class number 2 is 13 to 28, 36 to 53 and 23 to 40. So, this is based on the last 5 days rainfall, we will add up and we will find up that if this is the value for this, what is the rainfall that has happened, and based on that we will put it in a particular moisture class. So, 1, 2, 3 classes are there, and for each the millimeter values of rainfall is provided. And now we say that AMC1 means soils are dry, that is class 1, roughly the soil is dry, AMC2 is average condition, AMC3 is saturated. Now, all the curve numbers, that means and also the season is also considered, this growing season, dormant season, so on. The curve numbers are given for AMC2. That means for AMC2 conditions, all the curve numbers are given. So, if it is AMC1 or AMC3 for a particular area, there are 2 multiplication factors are given. I have not shown that, those are a little bit complicated equations, but these are standard equations, you can just multiply with that. where you can multiply with those factors and you can get for MC1 or MC3 what would be the curve number. You just need to multiply the curve number with that particular value and you will get that. So, that is the first step that you have to do, and then based on the soil surface, there are 4 classes of hydrologic soil group. You need to choose the curve number, that is group A, high infiltration rates, that is sand and gravel; group B, moderate infiltration, moderately coarse texture; group C, this is low infiltration; and group D, very low infiltration for clayey soils, soils with high water table, and so on. So, there could be 4 soil groups. Similarly, there is land use or land cover also changes, like there is fallow land, row crops, small grain, pasture range, woodland. So, this is mostly for, as you can see, these are mostly for maybe suburban areas or rural areas, not for urban areas. And practice in relation to hydrologic conditions, like what kind of agricultural practice such as contouring or terracing, rotation of crops, all these things also influence the curve number. So, let us see how the curve number is selected. So, you can see this particular table for different land use, land cover, different treatment practice, overall hydrologic condition, and hydrologic soil group A, B, C, D, we can choose the curve number. So, if it is a fallow land with straight row with poor hydrologic condition and soil and group as C, this 91 is the curve number for antecedent moisture condition 2. Now, if it is moisture condition 1 or 3, you have to again multiply it with the factors given and get to the actual curve number. Once I know the curve number, I will go to the chart, I will find the intensity for each intensity rainfall, what would be the amount of runoff that we can estimate, or we can put this directly into the formula and we can calculate the Q value as well. So, from the curve number, we can directly determine the total direct runoff as well, directly from using the curves as well. So, for watersheds with multiple soil types or land uses, area weighted CN could be calculated. Now, as you can see, these are not urban areas, these are for larger watersheds or agriculture areas. So, in TR 55, which is a report which is a report which is developed much later, the curve number selection could be also done for different urban areas like open space, impervious areas, urban districts, residential district. So, here also you can see that curve numbers are given as per the hydrologic soil group of that area. Like you can choose, like for a paved parking lot, the curve number could, based on the kind of hydrologic soil group, it could be 98. All the values are 98 because it is a paved area. But for residential area where there is some amount of average per impervious area, there is some consideration, you can see the curve number to vary because there is some amount of soil as well. So, that is how we can choose the curve number and we can pick up the values of amount of from the rainfall value, we can determine what would be the runoff value. So, this is one method and it is applicable using this chart. These are applicable for small urbanizing watersheds, but these are values for US. People have modified them for Indian use as well. But anyway, so this is one method. And from here we can determine the storm runoff volume, the peak rate of discharge, hydrograph, storage volumes, and so on. So, these are the things that we can estimate. So, the next method that I will discuss is the time area method, where we develop a rainfall hyetograph, and this hyetograph is actually used to create a rainfall hydrograph eventually. So, rainfall hyetograph shows the distribution of rainfall intensity over time. If you remember the rational method, we discussed that the different intensity during a rainfall event, because rainfall event doesn't happens for 6 hours, but the intensity of rainfall is not same throughout. So, there is different intensity for that during the entire event. So, that is not considered. A rainfall hyetograph actually shows the distribution of rainfall intensity over time, and this is represented by a bar chart like one given over here. So, how we use that? So, we divide the entire time period of TD, that is total duration of that rainfall, into delta T intervals, n successive time intervals of duration delta T. So, each of this time interval is delta T and there are n intervals. Now, what we do? So, rainfall hyetograph is basically prepared from the IDF curve. Now, For rainfall duration of 10 minutes, intensity of rainfall we find from our IDF curve as 151.38. For 20 minutes, it is 108.61. So, this is how we determine the, for different durations of rainfall, what is the maximum intensity from the IDF curves. So, once that is determined, then we need to determine the successive depth of rainfall, which is in millimeters. Now, this is millimeter per hour. So, for 10 minutes, we need to determine what amount of rainfall happens. So, that is 25.23, that is 151.38 divided by 60 into 10, right. So, that is 25.23. Similarly, for 20 minutes, we get this figure. With for 30 minutes, that is 89.44 into 30 divided by 60, that is half of that, that is 44.72. And in this way, we can see that for a duration of 120 minutes, total amount of rainfall that happens is 92.8 mm. So, this is the total depth of rainfall in millimeter, or this is the indicator of the quantity of rainfall. We would multiply with the total surface area to get the overall volume, but this gives us rainfall in depth. Now, as you can see that the more rainfall happens over time, like 10-minute duration, then 20-minute duration, gradually the depth increases, right. So, initially it is 25.23, then it increases by another 10.97, then it increases by 8.52. Based on these values, we just we subtract each one and we get that, and gradually we see that the increase is gradually decreasing. So, that means for the smallest duration, maximum amount of rainfall falls, then for longer duration rainfalls, there are also small volumes of rainfall in subsequent time intervals. So, these values that we get, we now reorganize them in such a way, so that the highest values goes into the center, and then the smallest values goes into the two edges, 4.27 and 4.08, and then we organize it as a bar chart. And when we do that, and for the different time intervals like 0 to 10 minutes, 10 to 20 minutes, in this particular order, we get this particular graph, where you see the rainfall is initially low, then gradually it increases, then gradually it again comes down. So, this is called a rainfall hyetograph, and this actually gives us the possible differences in intensity during a particular rainfall event, and how, based on the IDF curves or the maximum intensity for different time periods during that longer time interval, how we can consider this is a case where maximum kind of discharge has happened. So, intensity is determined from the IDF curve for each duration. Of course, over here precipitation depth is determined. So, these are all organized in a time sequence with maximum intensity at the middle TD. So, usually this value is taken, and then based on this value we can determine what kind of rainfall has happened during different time periods, and then we can convert it into the actual the quantity of water that is being generated, or the runoff that is being generated. So, next we show you the time area method, where we use this hyetograph that I just showed you in the last slide. We showed you how to estimate a hyetograph. Now, how do I apply that? Now, in the time area method, we apply this particular hyetograph, and it is an extension of the rational method, you can say. But only thing is, the method in this particular method, we account for the temporal variation of rainfall intensity, and this method could be applied to mid-size catchments, not very large catchments and neither small catchments, but mid-sized catchments. And this method transforms a storm hyetograph into a runoff hydrograph. I was saying at the beginning that hyetographs is to be converted to hydrograph. Hydrograph means the runoff, the volume of runoff, how it changes over time, and cumulatively we can determine the total quantity of runoff as well. So, that is an hydrograph for a particular point, for a particular area. So, hyetograph needs to be converted into a hydrograph. So, time area method is based on the concept of time area histogram of contributing catchment sub areas. So, we need to multiply the time of rainfall into the area for which that rainfall is valid. So, that has to be considered, and both time and area is considered to determine the total quantum of runoff for that particular area. So, over here, the time taken for surface flow to reach the catchment outlet is more for remote points and less for points near. This we have already seen during the rational method. Then time of concentration of catchment is divided into number of equal time intervals. So, if the total catchment time is 1 hour, we divide into maybe 6 intervals of 10 minutes, 10 minutes, 10 minutes and so on. Cumulative time at the end of each time interval is used to divide the catchment into zones delimited by isochrone lines. What are isochrone lines? Points from where flow takes equal time to reach the point of consideration can be joined, and these lines are called isochrones. So, let us look at this particular catchment. So, I have this is a isochrone line. That means, from this particular point, all these points, the time taken to reach the inlet is actually same. Similarly, for this particular isochrone, all points lying on the isochrone, the time taken by water to travel from these points to that particular inlet is actually same. So, that is cumulative time at the end of each time interval is used to divide the catchment into zones delimited by isochrone lines. So, if I have 1 hour and then I divide into 6 time intervals, that is of 10 minutes each. So, maybe this is the first 10 minute, then another 10 minutes, then another 10 minutes. So, that means, in 30 it takes 30 minutes for water to reach from this point to this particular point and so on. So, that is how we divide the entire catchment, and this has to be this is done for one inlet point. So, you can understand that this kind of calculation needs to be done for all inlet points, right. So, partial flow at the end of each time interval is equal to the product of effective rainfall into contributing sub area Q is equal to I into A. So, that means effective rainfall, that is rainfall minus the losses from evapotranspiration and all these things, into area, and we can also multiply a coefficient as well later on if you want to. So, area into intensity of rainfall into coefficient, that is the total volume of runoff that is being generated, and this at the end of each interval we need to compute that, right. And time intervals of effective rainfall hyetograph and time area histogram should be equal. So, time area, this multiplication of time into area, and the histograms and the hyetographs intervals, this has to be kept same, right, because we in hyetograph we get intensity for each of this interval, and those intensities are actually taken up. So, this is that area and this is time. So, this is for this first time period, second time period, third time period, fourth time period, this much area is comes in, then this in this time period this much area comes in, and so on. So, now let us look into the catchment. So, this is the overall catchment. So, these are the isochrones, like the first isochrone, the second isochrone, third isochrone and so on. The area varies, that means, in the first isochrone the area is less, A1 is much lesser than A2, A3 is again less than A2, A4 is probably larger than A3, but still lesser than A2. So, but these are the isochrones as per the time of travel, means the total water to travel both by either by surface or via the sewer. This is the maximum time that is taken. So, the first delta t interval, the first time interval is I1 rainfall over the entire catchment happens. That means, the first from hyetograph we know that the rainfall also this is hyetograph something like that, right. So, so first time interval is this one, so rainfall is less. So, we multiply that we know that this is the rainfall that came in A1 into I1. I am not showing the coefficient, of course. So, total discharge Q1 reaches this particular point. So, that is what is this is rainfall intensity I1, this is given. So, sorry, this is I did not see this. So, this is the hyetograph. So, this I1 is taken, then I2 is for delta t, and similarly we have got over here the cumulative area I1 into this area A1. Then for the next part what we have is in I2 time period in second delta t interval, discharge is A2 into I1. The discharge from this particular area immediately it takes time to reach this particular period. So, right now in the second time period, the water that is reaching over here is actually A2 into delta T, that is the first time period's water, right. The first time period, whatever rainfall happened in this particular area, it now reaches this inlet in delta 2. So, that means the rainfall is A2 into A1, whereas I1 into A1 into I2 for the first area. The second, because now we are considering the second delta T interval. So, that is why it is I2, we take I2 value from over here, but the water that reaches from this area is actually the intensity of the previous time period, that is why we are taking I1. So, A2 I1 into A1 into A2. Similarly, for Q3 it is A3 I1 into A2 I2 into A1 I3. We keep on doing that, and then eventually we see that Q5, Q6 is A4 I4 into A3 I3, because there is the rainfall may have stopped, the rainfall may also stop in between as well, and Q7 equal to 0. So, usually we see that the rainfall intensity is coming down, and in the fourth time period this value is coming in, and this that means there is no that is 4 A4 into this fourth time period, but this is now reaching, but already this value there is no rainfall at this point of time, right, because the rainfall has already stopped, but still water is now reaching at this particular point. So, that is what we have now plotted, this time area diagram. So, this is the period when all the I1, I2, I3, all the time periods are there, and we can see that the maximum time area is over here, right. So, this is the time area curve, and this is the basically when I connect these points, this becomes the hydrograph. That is how much water comes to this particular point. So, hydrograph developed by plotting discharges against time can be used for designing stormwater channels or conduits. So, here we can see initially the discharge is less, gradually it increases, then it further increases, then it reaches the maximum point, then probably it will again come down when we. So, this is the time period which you are seeing over here, then again the value may come down over here, and so this is for the point for which we will develop this particular this we will develop this particular the sewer design will be based on that. Now, this is the time period when the entire catchment is actually covered, but after that some amount of rainfall will still be reaching, but that is after the rainfall has stopped. So, there is no point of considering that. So, this is the maximum possible value that should come. So, runoff coefficients or other loss methods can also be used. That means, we can multiply this value with C, and then we can get the total water that is stormwater runoff that is generated during this for this particular point. So, that is how we can determine the total runoff using the time area method. So, finally, we come to the last method, which is called the unit hydrograph method, and this method hydrographs of direct runoff resulting from a unit depth of rainfall excess occurring uniformly over the catchment and at a uniform rate for a specified duration. So, that means, in this one we assume that we determine a runoff. Now that you know the runoff, that is gradually the water that comes to the inlet increases with time, and then it reaches a point. This is that maximum point that I was talking about earlier, and then gradually it again reduces. So, total runoff is this, the area under this curve, but the maximum is over here, right. So, in the previous slide we were showing you the maximum value. So, hydrograph of direct runoff resulting from unit depth of rainfall excess. So, after abstraction, whatever is excess rainfall which creates runoff, which is that unit depth, we consider only 1 centimeter of rainfall has happened. For 1 centimeter of rainfall which has happened uniformly over the entire catchment at a uniform rate, what for a specified duration, then what would be the this hydrograph. So, volume of water contained in the unit hydrograph, this is equal to rainfall excess which is considered 1 centimeter over the entire given catchment. So, that is catchment area A into 1 centimeter is the area under this unit hydrograph. So, you can understand, if instead of 1 centimeter we can have 10 centimeter of rainfall, we can just multiply that and we can get the value of that hydrograph. Now, if I assume that for the first time period we have got this as the hydrograph. For the second time period, we can have another hydrograph. For the third time period, we can have another hydrograph. So, we can construct this hydrograph for different time periods, and we can add them all up to get the overall hydrograph. So, over here, first of all, instead of 1 centimeter rainfall, let us assume that this is 10 centimeter rainfall for time period delta t, that like there are 5 time periods suppose. For the next time period, the value could be something like over here, because the time period changes, that is why we start from here. Then for the third one, the intensity may be much lower, it may be something like this, and so on. So, once all these hydrographs are developed for the different time periods, we can add all the values up, and then we will get the overall hydrograph for this particular inlet point. So, that is how we can determine the overall hydrograph for a particular area. So, this unit hydrograph method, as you can understand, this will vary for different watershed. So, UH is specific to a particular watershed, and for a particular length of time corresponding to the duration of the effective rainfall. So, this has to be created for a particular watershed, and once it is done, we can use this for any kind of rainfall event. We can actually use this unit hydrograph and create the overall hydrograph for that particular instance. So, unit hydrograph is a lumped response model. So, this is a term which you will see used many times. So, lumped models considers individual subbasins as a single unit, average value of watershed characteristics are considered, and distributed model subdivides each subbasin into smaller cells. So, either we can go for a distributed model or a lump model for determining runoff. So, in lump model, all the average values of the watershed characteristics are taken for the entire area, for all the subbasins and also on, whereas distributed model, each subbasin could be using different values. So, that is the difference between a lump model and a distributed model. Anyway, so unit hydrograph is a lump model, and as you can see, it has to be constructed for each area, for each length of time of rainfall, and for a particular watershed, and then that could be utilized for in subsequent time periods for different rainfall events. We can utilize that for determining the total runoff. So, there are many other methods that are also used. So, these are more complex methods. So, these are part of the rainfall runoff process simulation methods. So, we can use something called a nonlinear reservoir method. So, this is the method used in this software, SWMM software, and you will see that in this particular method, in this particular image, it is actually shown that we have got a reservoir where some amount of water is stored, which is ds, which is actually the abstraction, you can say. Then some amount of water goes down, which is infiltration. Then some amount of water becomes runoff, some amount of water evaporates, and then there is precipitation. So, difference between precipitation minus evaporation minus runoff minus infiltration and abstraction, that gives us the runoff value, right. So, precipitation minus evaporation minus infiltration minus ds, that is only this part, that is gives us runoff. So, this is used for estimating runoff quantity for single event or long term simulation of runoff, mainly for urban catchments. Inflow is from precipitation, losses from evaporation and infiltration, depression storage ds, initial rainfall abstraction, and ponded water above depth ds becomes runoff with outflow q. So, d becomes runoff with outflow q, and depth d changes per unit time, and that is the difference between inflow and outflow rate in the catchment. This is based on conservation of mass, that is total volume of water that falls on the catchment and that goes out, that is same. So, this depth changes as per the difference in flow rate of inflow and outflow, that is runoff and precipitation. And this method is used in SWMM software that we will demonstrate later on. So, this is and this SWMM software is made by US EPA. This is for calculating runoff, storm, flooding and all these things we can calculate using this software. Another method is the kinematic wave equation. So, in this method, overland flow is modeled as a white plane with very shallow depth of flow, laminar flow you can call a shift flow, and discharges from unit width of catchment is estimated for a given rate of rainfall and infiltration. So, this is for total discharge for each time step can be computed in shape of hydrograph at the catchment and catchment outlet by adding discharges from all unit. So, we divide the catchment into small units, and for each unit we estimate based on the rainfall and infiltration, we estimate the hydrograph, and we add up all those hydrographs for this particular for all the small units that we have divide the catchment into, and overall we add them up all to get the overall hydrograph for the outlet and for this particular catchment or for this particular point that we are considering. So, that is how we can estimate the overall runoff for this particular catchment area by dividing the entire catchment into small zones, and for each zone we determine this particular hydrograph for particular time periods and so on. So, these are the different methods that we use for determining runoff or determining this runoff at a particular outlet. So, to conclude, the SCSCN method is used to estimate runoff for long duration high intensity rainfalls over small drainage basins. Unlike the rational area method, the SCSCN method can consider antecedent moisture conditions and actually many more soil and other characteristics. The time area method can account for temporal variation of rainfall intensity and could be applied to mid-size catchments. So, that is the benefit of the time area method. So, there are many methods that are in use, and usually depending on the software that we would be using, several options would be available and we can use any one of the methods. So, these are some of the references you can use. Thank you.